Okay, this is part 3 of lesson 1. We're going to wrap up lesson 1, the videos for lesson 1 and characteristics of functions. And so hopefully you have gone ahead and identified all the pieces for this function. And we'll go ahead and do this to see how you did. So the domain for this function, -6, it goes from -6 to 11, -6 to 11, and since both endpoints are included, then we use brackets. The range for this function is the smallest y to the largest y, and the lowest point on the graph is this point right here. So the lowest point has a y value of -3, and the highest point, maximum in this case, would have a y value of 4. And since they are both included on the graph, then we will use brackets around that interval as well. Intercepts. Now here's something I've added in. What do we mean by intercepts? We're talking about the x-intercepts. Here's an x-intercept, here's an x-intercept, here's an x-intercept, but also not only the x-intercepts, but we're also including the y-intercepts. So this ordered pair for this x-intercept is -3, 0. We have the y-intercept at 0, 3. We have another x-intercept at 6, 0. And we have a final x-intercept at 10, 0. Now remember, these are just points, so we always put points, x, y values, in parentheses. All right, so using the graph, what do we find f of 2 to be? In other words, what y value is associated with the x value of 2? What's 2's partner? So going to the graph, I'm going to go to the graph and the point on the graph where x is 2, and we get a y value of 4. F of -5, 1, 2, 3, 4, -5, that y value is -2. And then f of 0, go to the graph to the point where x is 0, and we get a value of 3. Okay, so it's just a matter of finding a y value for a given x value. All right, now looking at this graph, let's identify local maximum and local minimum. So remember, this is where you have a change in direction. So the function here is increasing, and at this ordered pair, remember this is a point, the graph changes from increasing to decreasing. So this is a local maximum. So we have a local maximum at 2, 4. Then this low point here where the graph changes from decreasing to increasing is a local minimum. So that occurs at 8, -2. Now let's identify the intervals. Remember, this is going to be a set of x values for which f of x is greater than 0. So how do we determine that? From your graph, identify where the graph is above the x-axis because where the graph is above the x-axis, the y values will be positive. So this portion of the graph, the function is above the x-axis, or the y values are greater than 0. But don't overlook this little piece here. The graph here is above the x-axis as well. So our intervals for which f of x or y values are greater than 0, they start at -3, and this interval ends at 6. Remember, parentheses, because at -3, the function f of x or the y value is not greater than 0, it equals 0. So we have to use parentheses. Same thing around 6. Then we have another interval, a small interval starting at 10 and ending at 11. All right, now remember, what are we going to do with 11? Because the point at 11 is above the x-axis, that means the y value, which is positive 1, is greater than 0. So we're going to show that by closing that with a bracket. Okay, what about the intervals for which f of x is less than 0? Now we're looking for the intervals where the graph is below the x-axis, which is here and here. So the function, the x value or the function begins at -6, which is below the x-axis. So I'm going to start with -6, and because the y value is negative or less than 0, I will put -6 in brackets. Then this portion of the graph stops being less than 0 at -3. So I'll close that with parentheses. And then at 6, the graph, that's where you have an x-intercept, so your y value equals 0. But after that, it becomes less than 0. And then at this x-intercept, 10, the graph stops being below the x-axis, or the y value stopped being negative. So I'm pretty sure that took care of my greater than 0, my intervals where the function is greater than 0 and less than 0. Now let's talk about the intervals in which this function is increasing and decreasing. Okay, so let's talk increasing. So on this portion of the graph here, from here to here, between these two x values, the function is increasing. So at -6, the function, the smallest value of the domain, it's in parentheses, increases until it reaches the x value of 2. At x equals 2, the function begins to decrease until it reaches the x value of 8. And then at 8, the function begins to increase and continues to increase until it reaches the x value of 11. Increasing and decreasing always get increasing and decreasing always uses parentheses. You'll never use brackets with increasing and decreasing, because at a point, at that x value, the graph cannot increase and decrease. It can't increase at a specific point because it's stationary. Same thing with decreasing. All right, so let's wrap this up. Let's wrap up this particular lesson and the videos for this lesson by talking about symmetry and what implications symmetry has on the graph of a function. So we kind of talked a little while, or in the first video, I think, for this lesson, about even functions and odd functions and having, determining even and odd functions based on symmetry. So when you have a function that is considered an even function, there will be symmetry with respect to the y-axis. So if we look at this example right here, this graph has symmetry with respect to the y-axis. In other words, if you were to take this graph and fold it over, this portion of the graph would lie directly on top of that one and vice versa. Okay, so now let's talk about another aspect of even functions. If and when a function is even, there is symmetry with respect to the y-axis. Because of the symmetry, then if you have a point on the graph, x, y, let's say, and let's focus on this one, this point right here is 3, 0, then because this function is an even function, then you know that there will also be a point the opposite of x, y on the graph. So in other words, since 3, 0 is a point on the graph, the opposite of this x which turns out to be -3, 0 will be on the graph as well. So even functions, for any given pair of x's, they will have the same y value. Okay? All right. Then let's talk about another aspect of even functions. So this is a more analytical, and this is kind of more abstract way to talk about a function that is even. But if a function is even, then the function evaluated at let's say a negative x value, its y value will be the same as the function evaluated at the x value. The two y values, the y values will be exactly the same. So notice on this function here, my x's are opposites, but these 2 points have the same y value. So that's what that means, and we'll emphasize this as we look at some examples. All right, so now let's talk about odd functions. Odd functions are going to be functions that have symmetry with respect to the origin. And of these examples that we look at here, this example here is the only one that has symmetry with respect to the origin. That means that if you were to take this graph and rotate it 180 degrees about the origin, the graph would have symmetry. So this portion would lie on top of this portion. So that a function that is odd will always have symmetry with respect to the origin. Okay, so another characteristic of odd functions will be this. If you have a function that is odd, let's say this portion, let's say that this function right here, the point is, and I know I didn't put it in the exact spot, but let's just say that this point is 1, 1, then it has a partner on the graph that is the opposite of the x value and opposite of the y value. So if xy is a point, such as 1, 1, then -1, -1 will also be a point. So when you have an odd function, you will have pairs of points that have opposite x's and opposite y's. All right, and then to look at this or describe this in a more abstract kind of way, then in an algebraic approach, if f of -x, if a function is odd, then f of -x will be the opposite of f of x. Okay, and I will kind of emphasize what this looks like in just a few minutes. So let's say we want to determine if this function is an even function, odd function, or neither. Okay, so how do you determine that graphically? Well, let's think about this. We know what this looks like, or let me say we should. So graphically, this is a quadratic. It has its vertex or its local minimum at 4, and the graph will open up. So hopefully we recall from earlier, the graph of this quadratic would look like this. And visually, this graphical representation, you can see the symmetry. The symmetry, this is an even function, and because this point is on the graph, then it will have a point where this is, let's call that -x, y, then this would be +x, y. They have opposite x's, they're directly across from each other, but they have the same y values. Okay, so what does that look algebraically? So algebraically, we have our function, f of x equals x² + 4. And if I needed to prove that this is an even function, then I could substitute the opposite of x. What's the opposite of x? Negative x. Everywhere I have an x, and then clean this up. So if I take a negative x and I square it, when you square the negative, you end up with positive. When you square the x, you get x squared plus 4. So f of negative x, notice that you end up with the same as what you started with. So f of x was equal to x squared plus 4. F of negative x equals x squared plus 4. So therefore, this is an even function. Okay? All right, then let's talk about, let's look at this function. So f of x equals x cubed. I want to know if this is an even function, odd function, or neither. So what does this graph look like? Well, this is a cubic function, and this particular cubic function looks like this. Okay? And graphically, if we have a point, let's say that this is a point 2, 8. Let's say we have that point, then there is a point -2, -8 on the graph as well. And that is true for all of these points. Okay? So, algebraically, what does that look like? So if I take my function, f of x equals x cubed, and we substitute negative x, then let's talk about what we end up with. When you cube a negative, when you raise a negative number to an odd power, that negative stays negative. And then, of course, x to the third power is x cubed. So compare, when you compare f of negative x to f of x, then look at what you ended up with. So f of x was x cubed. F of negative x was negative x cubed. Notice that these three things are opposites. So odd functions have symmetry with respect to the origin. If, or not if really, but if a point on the graph of an odd function is xy, then we know that there will be a point negative x, negative y on the graph. And f of negative x will be the opposite of f of x. And so these two are opposites. So even functions and odd functions, there are the characteristics. Let me turn my paper. All right, so now let's look at just a quick example. What about this? Is f of x equals x squared minus 4x plus 4 an even function, an odd function, or neither? And I guess I should put up here that this is an odd function. So again, how do you determine if this is an even function, odd function, or neither? We'll look at graphically in just a minute. Let's just jump into the algebraic approach. So algebraically, this would be you will substitute negative x everywhere you have an x, and then we're going to clean the expression up. So f of negative x will equal, what do you get when you square a negative x? You get positive x squared. What do you get when you multiply negative 4 by negative x? You get positive 4x and then plus 4. Okay, so now what we want to do is we want to compare this expression with this expression here. Are these two expressions the exact same? And the answer is no, because of this sign and this sign. Okay, so these are not the exact same function, so it's not even. This is not an even function. Is this expression the exact opposite of this expression? And the answer is no. In order for this expression to be the exact opposite of this expression, each sign would have to be the opposite for each term. The signs of each term would have to be the opposite. So this is neither an even function nor an odd function, so this is a neither. Now let's talk about this from a graphical perspective. You know that this is a quadratic. So because this is a quadratic, you know it's a parabola, and you probably even know that it's going to open up. Graphically, if I wanted to clean this up a little bit, f of x equals x, that would be x minus 2 squared. So this graph would look like this. It would have its minimum at positive 2, it would open up, and the graph would look like this. Now, does this graph have symmetry? Absolutely. There is an axis of symmetry, but the axis of symmetry is not with respect to the y-axis, and it is not with respect to the origin. So therefore, this function, even though it has symmetry, is neither even nor odd. So that's the relationship between, those are characteristics of functions that are even and odd. And I like to refer to odd functions have symmetry with respect to the origin, O, 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 and your x, your y values are opposite. Odd, origin, opposite, O, O, O. Okay, so that's going to conclude the third part of the video series for lesson 1. And we will wrap this up.